Thank you, Rich. And thank you, everybody, for being here. It's really exciting to have the chance to come and find out everything that's happening in this really exciting community. Before we get too far, let me check the sound. Does it sound good all the way in that corner? And in the back here and way over there? Excellent. I think we're good. Okay. If this were a standard talk about software research, it might begin with a little sermon about how we have no idea how to build software that actually works, and I would go on at length about huge projects that are late and over budget and not working at all, and security vulnerabilities and malicious hacking and medical devices that hurt people and rockets that blow up. But if you look around, sure, there are plenty of problems. But the thing that's amazing is the amount of software that does work. We build huge, intricate software systems. We distribute them across the globe. They handle vast amounts of data at lightning speed. So how did we manage that? Of course, there's no single answer. And some people, including me, probably including many of you, would point to the better programming languages that we have at our disposal nowadays compared to 10, 20, 30 years ago. Others would point to better ways of thinking about organizing software teams and getting things done. Other people would point to the incredibly powerful and stable and long-lived platforms. Think about Windows, if you like that, OS 10, Linux, Apache, the JVM, on and on and on. We can stand a lot higher than we used to be able to. And here's another one that you might not have put on this list initially, but it's actually the subject of the talk. We have gotten a lot better at specifying, that is to say, rigorously thinking about what software does. So why are specifications of software useful? Well, duh. If you want to know what the software, if you want it to work, then you want to know what it does. And it's useful to think about that. We are going to get past the well duh stage in this talk. But here's a well duh specification. So here is a specification of the simplest possible piece of code you could write. It says the sort function takes a list of things and it returns the list of the same things in increasing order. Couldn't be simpler. This is a useful thing already. And writing it down might have made you think about some aspects of sorting that you could initially overlook. But there's a few things to criticize about it. First of all, aren't we past sorting functions now? This is a pretty simple thing. Also, aren't we past writing down specifications in English? English is hard to understand and ambiguous, and you get into endless arguments. Here's another criticism, and for me, this is maybe even the most important one. This specification has nothing to do with the sort function that you wrote. Or maybe it does. If you sit with one on one hand and the other on the other hand, you can look at them and see some correspondence. But as soon as you think about it and say, oh yes, that satisfies that specification, and then as soon as you edit your sorting function, all bets are off. So there's no, the specification is not live. It's an inert thing that's disconnected from the code that you write. And that is less useful. Okay, so here are 3 dimensions of discontent. And what we'd like is to move to the other end on each of these dimensions. And of course, this is a decades-old area of intensive effort, and people have moved to the other end in some pretty amazing ways. So we have things like the C language reference at 600 or so pages, Java at around 800 pages, C++. Anyway, we have architecture reference manuals that are huge. We have specifications for things like standardized architectures for the innards of automobiles, and those run to thousands of pages. So we are not anymore just specifying the sort function. We are way past those days. We're also past the days of writing down specifications in English. Some specs are still in English, but people are getting very good, and there are decades of experience in designing really great languages for writing specifications in, and for writing large and complex specifications in those languages. So we have the development of lots of environments for being precise about specifications. And we have decades of research in tools for connecting specifications to verification, to code. And the most obvious way to do that is verification, by which I mean writing a mathematical proof that the code satisfies the specification, and better yet, writing it in a form that a machine can check. These are power tools. They're not super easy to use, but with a little bit of training, people can use them to do absolutely amazing things. We'll see some of those. Okay, so we started out with this cube, and our sorting specification is down in the simple, disconnected, informal bottom corner, and we've seen that people are moving into the other corners. But of course, where we'd like to be is in the far corner. So we'd like to have specifications that are simultaneously integrated with the code, rich and describing very interesting properties of the code, and completely formal. And I like to call those deep specifications, specifications with those three properties. So this all sounds fine. I hope it does. But you might be wondering, is this possible? So we've seen people moving along one dimension at a time. But could you possibly move along all three dimensions and get to the far corner? Is that a total pipe dream? Even as recently as 15 years ago, a lot of people would have said, yes, that's a pipe dream. We're never going to get there. We can keep trying because it's important, but we're not going to be specifying, we're not going to have live specification of the real code of large systems anytime soon. And they were wrong. So things started happening. Amazing things started happening about 10 or 15 years ago. One of the first that people like to point at is the CompCert C compiler. So CompCert is a compiler for the bulk of ISO C99. So it accepts most of the standard C language. It compiles code for PowerPC, ARM, and x86 processors. It is not quite as fast as GCC, but not too bad. And it is 100% fully verified, end to end. Totally amazing to me. Here's another, in a way maybe even more amazing. SEL4 is an operating system, a microkernel operating system, which is nowadays deployed in cell phones, which comes with an end-to-end proof. Again, this is a nothing up my sleeve proof that the actual machine code implements a high-level logical specification. The specification is quite rich. It describes all of the behavior of an operating system. It runs about 200 pages. And there's a machine check proof that the two correspond. Moreover, the tools are getting better. So we have, on the left-hand side, very powerful proof assistance. We have the development of fancy new program logics that make it easier to reason about how code behaves. On the right-hand side, we have the influence of SMT solvers, which are unbelievably powerful tools these days, and people are using them for much lighter weight verification efforts. And we have many more examples of real software with rich, live, and formal proofs connecting it to specifications. So we have verified compilers. CompCert is a compiler for single-threaded programs. We have CompCert TSO for concurrent programs in C. We have CakeML, which is a verified ML compiler. Bedrock is another low-level language. We have verified operating systems now, several of them. We have verified file systems. We have distributed systems verified verified in such a way that the code meets the actual running code meets the spec. We have verified cryptography. So what I take from this is that deep specification and verification of real software is shifting now. We're seeing the beginnings of a sea change from a collection of heroic tour de force point efforts to the beginnings of an engineering discipline. So that sounds great. Where's it all going? Are we, in particular, headed for a world where all software is formally verified and specified? Well, no, I don't think so. Verification will continue to be a somewhat expensive activity. We'll continue to use it mostly for very critical components of the software stack. But a world where pretty much all critical components are verified and other components are written in much safer high-level languages than what we use now, like, for example, Clojure, is no longer science fiction. In fact, all of this is something that I'm working on very actively with some fine collaborators at Penn and elsewhere. And one thing that we're very interested in is trying to build this zero vulnerability, fully verified software stack that I alluded to a minute ago. So we and many other people are hard at work on every piece of this picture, and I expect to see the results in widespread use in the next decade, I'll say, going out on a limb. So I will sleep better when that happens. But in the meantime, some of you may be asking yourselves a question. I just want to write code that works. I don't want to write proofs about it. I'm just a hacker. I don't want to go to graduate school and learn to do logic and all that stuff. So is this talk really for me, or should I read my email or go outside? Well, I hope you stick around, because what I want to show you for the rest of the talk is that the idea of deep specification can be used in other ways than for formal verification. So the first example is type systems. Type systems used to be everybody's favorite example of lightweight formal verification. What do I mean by that? Well, a type that you assign to a program or a collection of types that you assign to a module is a kind of specification. It doesn't qualify as a very deep specification for me because the properties that types describe are generally quite shallow. They talk about the shapes of things so that they can be verified statically whenever you compile by a fairly straightforward algorithm. Nevertheless, type systems are a runaway success in terms of improving software quality because they're always on. And they give you some assurance and some checking for very little cost. Nowadays, the things that people are doing with type systems are becoming much more deep. So those of you that have dipped a toe into the Haskell world will know that the type system of Haskell is gradually drifting toward being really a program specification logic. And a lot of the developments in the Haskell community and the technology of Haskell type checking have been pushing it in that direction. So Haskell programmers right now can shoehorn a lot of information about what their program does into the type that the type checker checks. So this is very cool. But you might have another question. We're at a Clojure conference. Clojure is not a typed language, perhaps yet. So is there another way to use specifications that you might find more directly useful in your day-to-day work? Yes, there is. So another way to use specifications is for random testing. And the idea here is, again, to get pretty good assurance to get some help with debugging our code, not to completely verify it down to the last iota, but to get some assurance that, that we have understood what it's supposed to do and that it does that. Let's go on. So the idea is that we write down our specification as a set of executable properties. So the specification is written down as a program. We generate many random inputs and check whether the specification holds for each one of those inputs. And if we generate enough inputs, and if they're well distributed, then we may find a lot of bugs. And when we start slowing down on finding bugs, this may give us a good degree of confidence that the software is working as intended. The third idea that I won't go into in too much detail because there's no time, but these specification-based random testing frameworks need to pay a lot of attention to the issue of shrinking. So I'll quickly tell you what it is. If you generate a lot of random tests and wait for one to fail, you're probably going to come up with a test that includes a whole lot of garbage, right? Because it's just a random thing. It's probably huge. And only tiny pieces of it are actually necessary to exhibit the failing behavior. So what random testing frameworks of this sort do is once they find a failing test, they start rerunning the test, pulling out small pieces of it. So they say, well, let's delete that bit and see if it still fails. If it does, let's delete another bit and see if it still fails. So they iteratively make the test smaller until they can't find any bits to delete that yield a test that still fails. When you've done that, you have a test that is likely to be minimal for illustrating a counterexample. So effectively what we're doing is moving from unit test suites to property suites plus generating random inputs and shrinking counterexamples. So back to our sorting function. Up on the top is the unit test suite that you might write. So it says, well, if you sort the list 1, 2, 3, that should return 1, 2, 3. And if you sort 3, 2, 1, that should return 1, 2, 3 again. Now, this is fine. In fact, it's pretty good. So I'm a big fan of unit testing. It's good for a couple of reasons. It helps find bugs, but also it makes you think about what the program is supposed to do. And that is basically a specification activity. So it makes you think about what the specification should be and then generate test cases from that. The problem is, the downside of unit test suites is that you do all this work, you write down a bunch of tests, you have to think about the specification as you're doing it, and then you throw away the specification or flush it from your working memory, and you just keep the tests. So that later on, if somebody wants to understand what the specification is, they either have no hope or they have to re-derive it from the test that you wrote, or maybe you wrote some comments. But wouldn't it be so much nicer just to keep the specification and generate the unit test from that? So that leads us to something more like the bottom, where we write down, okay, the sorting function should take a list of things and return an ordered list. That's the first property, prop ordered. And then the second list is it should take a list of things and it should always return a permutation of the original list. And when you put those two together, that's what we mean by sorting. Oh, this bottom example isn't in Clojure, is it? I'm sorry. Let's, okay. That's better. Okay, so this notion of specification-based, or often called property-based random testing, was first popularized in 1999 by Kuhn Klassen and John Hughes. Their tool was called QuickCheck. It was written in Haskell, but it was quickly ported to every language that you can imagine, including, of course, Clojure. So you can view this whole talk as actually an advertisement for test.check in case it needed one. So you can find ports of QuickCheck to just about every language that you might happen to be working in. There is a company, it's called QuickCheck, that markets not only the Erlang port of QuickCheck, but also consulting services using QuickCheck to find bugs in real software, and it has been used to find bugs for telecommunications companies and car manufacturers and distributed databases and so on and so on. So what I would like to use the end of the talk for is to give you a little tour through a QuickCheck specification that I wrote along with John Hughes, co-developer of QuickCheck, and Thomas Artz, co-founder of Qvik. And the software that I'm going to specify is Dropbox. Now, you might ask, why do we want to specify Dropbox? Here's my answer. First of all, it isn't just Dropbox. There are many synchronization services out there. 6% of the world's population uses Dropbox alone. If we add in the next biggest two, then it's 10%. And all of these, whatever it is, 1 billion people or so, are entrusting these services with all of their most precious data, including possibly their closure code. So I think I would like to see a specification. So the goals will be, we want to write down a precise, mathematically precise specification. It will be written down, since it's a QuickCheck specification, it will be written down in the form of some Erlang code that can test the correspondence between an input to a synchronization service and the observation that we make of its behavior. So we want the specification to be phrased from the point of view of users of a service for two reasons. One, because we are users of Dropbox. We don't work for Dropbox. So we'd like to know how it behaves as users. And also because since Dropbox is effectively implementing some kind of distributed file system, every other synchronizer out there should probably have more or less the same behavior. So a specification that we write for Dropbox should be usable with maybe minor tweaks to test not only Dropbox, but lots of other tools that are out there. Okay, so we're going to write down a specification, and we're going to validate it by comparing it, by using QuickCheck to test whether Dropbox actually behaves that way. So the setup of our tests is very simple. For the moment, we can run our tests just on one laptop. That makes things easy. On that laptop will be an Erlang process. It's the controller of the tests. So it's the thing that is distributing commands to the various nodes, saying, try writing this file and now see what the file system looks like, and so on. Those different nodes are running as virtual machines on the same laptop. And in each of those virtual machines is a little Erlang stub that's communicating with the master and executing the commands that it says. Also on each of those VMs is a Dropbox client. We had nothing to do with that. We just installed the standard one. And each of those is communicating over the network with some servers that Dropbox owns. Okay, so this is the testing setup. And here's the idea of the test. So we have, let's go back one. All right. So we have the system under test. That's what I just showed you. And we have a model of the system under test. That's the specification that we're going to write. And a test is going to be a sequence of operations, things that we do to the file system. When we run the test, we're going to execute each of those operations by really doing things to the file systems of the different VMs. And each time we do, that's going to give rise to an observation, what we see when we execute the operation. And now we're going to define the model as a little state machine. So it's going to have transitions corresponding to legal observations. And what we want to see is that each of the observations that we make when we run the test is allowed by the state machine defined by the model. If we reach a state where the next observation doesn't match anything that the model can do, then that's a failing test. Is that a bug? Notice I said failing test, not necessarily bug. Is it a bug, or is it an error in the specification? A priori, could be either one. So you have to look at the specification, look at the behavior, and decide which one you like. So the basic form of the specification, I'll refine it in a minute, but the basic form of the specification looks like this. If we have some sequence of operations, read this, write that, then we execute it, and it gives rise to some sequence of observations, then what we want is that from the initial state of the model, the transitions implied by those observations are a valid sequence of transitions for the model. So this is the specification, written in English, not Erlang, of what a synchronization service should do. Of course, there are some details to fill in. So first of all, we need to think about what operations do we need and what observations do they give rise to. Here's the first try. So the operations are read and write. And the observations are when we do a read, okay, so read and write, each annotated with the node, the client node that we're doing the read or write on. So if we have 3 VMs, then we can do read from 1 and then read from 3 and so on. So read on a particular node is an operation, and write a new value on a node is another operation. The observations that we make are when we read from a node, we observe the contents of the file. When we write to a node, we observe the previous contents of the file. So we're going to implement the write operation by actually doing a read and then quickly writing the new value. And this is important because the specification is going to want to know what is the value, is going to want to talk about the value that was overwritten by the write. Now, you might be wondering something. I'm not saying here which file I'm reading or writing. And for present purposes, for purposes of this talk, I'm going to make a small simplification, which is that there's only one file. Now, is that a ridiculously small simplification? Does it make the specification uninteresting? No, we can still find bugs. Okay, so I'm just gonna, there will be one file, and I'll be reading its value and writing new values into it. And I'll use a special value, so the value in the file will be a string generally, but if the file hasn't been created yet, if this is before the first write in a test, and we do a read, we'll get back a special value called missing. And if I write the value missing into the file, what that means is delete the file. Okay, so really the operations are read, write, and delete, but I'm going to squash them into 2 just for brevity. Okay, so this is the basic set of operations, but there are a couple of challenges that we're going to need to deal with before we can get too far. The first challenge has to do with conflicts. I've been in the synchronization business for a while. I wrote a synchronizer called Unison back in the 90s. And it, for a long time, until we did this work, it was the only synchronizer that had a formal specification. Now there are 2. And from that experience, what I can tell you is that the hardest thing about synchronization is conflicts. Everything is pretty easy as long as nothing happens, as long as there are no conflicting changes. As soon as there are conflicting changes, you really have to think hard and things get subtle. So what do I mean by conflicting changes? So here are 2 nodes, and on the first node, we write the value A into the file. And very soon after, before the second node has had a chance to hear from the first node via the server, it writes the value B. Now, sometime later, the second node gets the message that the first node wrote A, and now we have a problem, and we have to do something. So what do? Different synchronizers do different things, but a reasonable answer, and the answer that Dropbox chooses, is to say that the earlier value wins. You could argue with that. You could say, well, why not have the later value win? But this is what they do. So the earlier value wins, that is, the value that the server heard about first wins, and the other value, B in this case, will get moved to a conflict file in the same directory. So it'll get moved to a file whose name is blah, 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 conflicting version at such and such a time. So it sounds like we should write down, it sounds like maybe the write operation should observe not only the value that wound up in the file, but also maybe some conflict files. No, that's not what we want. And the reason is that Dropbox actually has a kind of a funny behavior here. So these conflict files, the file containing B, actually doesn't show up for a little bit. So when the second node hears about A, it changes the value in the file immediately to A, and B just disappears for a short time, a few seconds, assuming your connection to the server is good. And so if we tried to observe the effect on conflict files immediately after the write, as in fact an early version of our specification did, it would look like the behavior is wrong. Since we want to match Dropbox's actual behavior, we need to do it a different way. And the way we do it is by adding one more operation. We call it stabilize. And what it means is we wait for a little bit until the same value is in the file and the same set of values is in conflict files on all of the nodes. So we wait for everything that's going to happen. And then what we observe is the value in the file and the set of conflict values. Okay, so this gets us going with dealing with conflicts. But there's one more challenge, and that is non-determinism. So the issue is that the Dropbox client is looking at the file system, and we're effectively using the file system as the API to indirectly communicate with the Dropbox client. So we're writing stuff into the file system, and it's noticing pretty soon after. But it's also interacting with the Dropbox server at times of its choosing and in ways that we can't see. Moreover, the timing really is completely unpredictable. So it isn't that you write something in the file and then after a certain fixed length of time there's a communication with the server and things happen. It can really be from very quickly to a very long time. So we have this invisible, unpredictable activity in the background. That is to say, the system that we're testing is non-deterministic, is inherently deeply non-deterministic. So we need some other approach. We need to enrich our approach. There are different ways to do this, and we experimented with several. And the way that we wound up with as being lightweight, natural, easy to understand, and possible to use for testing was simply to model the interactions between the Dropbox clients on each node and the Dropbox server as explicit operations, as explicit observations, not corresponding to operations that we include in tests. Okay, so now things are getting a little bit subtle, but stay with me. So the final version of our set of operations and observations is this. The operations are as before. The observations include the three that we talked about and two kind of pseudo-observations, which we don't actually observe. We don't see the server communicating with the client, but we can conjecture them. So the final specification looks like this. We take the test, which is a series of operations. We run them to gather observations. Now, between each pair of actual observations, we insert some number of conjectured observations of ups and downs. So up is the client saying to the server, here's what my state is, and down is the server saying to some client, here's what your state should be. So we insert some sequence of ups and downs. And the important thing to think about is there can only be finitely many of them because it's only interesting for each client to communicate with the server twice, one up and one down. So that's what makes testing still work. So inserting all of these ups and downs gives us an explanation, a potential explanation for what we saw. And we run that explanation against the state machine that's encoded in the model to see if the model says, yes, that's a valid explanation. Here's an example. Suppose this is our test. So we write A on client 1, we write B on client 2, then we read on client 1, and then we write C on client 2, and then we stabilize and see what's happening. Okay, so that's the test sequence. When we run that test, one sequence of observations that we might make is when we write A, we see that the previous value on client 1 was the file wasn't there. Then when we write B, we see that the previous value was A. That means that there must have been a communication from client 1 to client 2 via the server in order for that to happen. But we're not seeing it in the actual observations that we made. The explanation that we can generate, or an explanation that we can generate, one of the valid explanations that explains this sequence of observations is client 1 does a write, then client 1 does the up action, then client 2 does down, and then we get the actual observation that we made, that we see A, and so on. Okay? So this is our specification. This is our real specification. Now, how do we use it for testing? Well, we just have to turn it on its head. So the specification that I gave said, this must be the case. To test it, we just generate a lot of test sequences and check for each one, is it the case? And if it isn't, so that is to say, if for every interleaving of ups and downs with the observations that we actually made, the model says no at some point, there's no transition from a state that we reach, then that's a failing test. All right, I am running short on time, so I'm not going to tell you the details of what the model looks like. There's a paper about this if you're interested. It's pretty simple, though. So the states of the model are, we need to keep track of the global stable state, that is the one that the server, the value of the file that the server knows. We need to keep track of the global conflict set, so the set of conflict values that the server has heard about. And then at each node, we need to keep the local value of the file and 2 bits. One saying whether that node is fresh, that is, it's heard from the server recently, or stale, that is, the server has something newer, and whether the node is clean or dirty. Dirty means that it's been written since the server heard from it. And given all that stuff, we write down specifications of steps that the model can take in the form of preconditions and transformations on the state. So there's one for read, one for write, one for stabilize, one for down, and one for up. And the one for up, as you might kind of expect, is the most complicated. I won't go into detail, but this was not our first specification. It required some refinement, and we refined it as a result of failing tests that forced us to think about, oh, Dropbox is doing something a little bit more subtle than what we realized. In particular, 2 things that you could read here if we took time to unpack the notation are, if 2 different nodes, without talking to each other at more or less the same time, write the same value into the file, no conflict. Second, if one node writes a value into the file and the other node deletes the file, no conflict. The deletion loses even if it makes it to the server first. Interesting, a little bit interesting. Here are some more interesting things. So here is an observation showing that Dropbox can delete a file that was just created. So let's see what happens. So we create the file on client 1. We put the value A. We then delete it on client 1 by putting the value missing. On client 2, we observe the creation. So notice that client 2 has not heard about the deletion yet. On client 1, we create the file again. And finally, we read and notice that it's gone. OK, well, what happened? Well, don't worry, it will be back after a little more communication with the server to stabilize things. So, is this a bug? Maybe not, probably not, but it certainly surprised us when we found it. One interesting thing here, just a footnote, is that the timing of the operations here is very critical. So if you just blast out all these operations as fast as you can, you won't exhibit this behavior. You have to do it in a fairly carefully timed way. So the thing that I'm not showing you is we actually have one more operation. It's called sleep. And so when we're generating random tests, we're generating sleep for random lengths of time. When we're shrinking tests, we try to shrink the sleeps away or make them as small as possible. And that allows us to generate short tests. If we didn't have sleep, we could still get this behavior, but you might need a test of 10,000 writes or something like that to wait the right amount of time. So sleep allows us to have short tests that trigger timing-dependent behaviors. OK, second surprise. Dropbox can permanently recreate a deleted file, even if you're only doing things on one client at a time. OK, so there are other clients, but they're idle. So what do? You write B, creating the file. Then you delete the file at just the right time. And then you wait a little bit and read the file and notice that it has come back. And this time, it doesn't actually stabilize to what you might think. The file is back for good, and the deletion got overwritten. Here's another surprise. So what happens here? So we create the file on client 2. We write B into it. Why is it client 2 now instead of client 1? Because we created these randomly. OK, so we create the file on client B. We overwrite it on client 1. And again, the timing here is very critical. And notice that, the write sees the value B. In fact, the timing that we need to use is we need to overwrite the file as soon as it arrives, while the Dropbox client is still doing some stuff. OK, so we wait for the file to arrive and then immediately overwrite it, and then read it again, and notice that we have actually we read the value that we wrote. But now we try to stabilize. So in the stable, quote unquote, state, so you wait for a long time, and nothing changes. And in the stable state, the new value persists on client 1, and the old value persists on client 2. So why is that bad? Further investigation reveals that client 1 believes that it is fresh. In other words, if we overwrite B on client 2, then A disappears without going into a conflict file. OK, so that's a data loss bug. Right. There are many details of all of this in the paper that you can find on my webpage. Where are we going with this specification effort? Well, of course, we would like to, we believe that there are probably more bugs to be found. And from experience with Unison, we expect that adding directories will flush some more out. So So what we're working on now is adding directory structure and generating tests involving multiple files and directories. And the other thing that we'd like to do is test lots more synchronizers. This takes a little bit of, every particular synchronizer that you pick up takes a few days of messing around with the test harness because synchronizers are kind of finicky beasts. I'll tell you one difficulty that we had with Dropbox. When you're trying to generate random tests and you want to generate a lot of them and execute them very quickly. So what kind of workload does that mean for the Dropbox, the machines that are running Dropbox? What they're seeing is lots and lots and lots of changes to the file system as fast as we can generate them. What do you think Dropbox does when the client sees that kind of activity in the file system? It backs off. It backs off and batches the communications with the server so as not to overload the link. But that's exactly wrong when you're testing. It's exactly what you don't want. So there's a lot of this kind of back and forth of, how can we cajole the system that we're testing into behaving in a way that we can follow. Lots more is described in the paper. But for now, let me just say that I hope I've given you a sense of the excitement I feel in some of the ideas that are now becoming real, both in the area of specifying and verifying real software systems, and in the equally hot area of property-based, specification-based random testing. So thank you very much for your attention, and I'd be glad to answer questions.